Now I want to talk about a new technique that can be applied to differentiation called implicit differentiation. All the differentiation we've done so far has been, I guess, what you could call explicit because all of our functions have been written explicitly. In other words, they've all been written in the form y equal to. They've been specifically solved for y. So if you had something like square root of the sine of x, and you want to take the derivative of that and say y prime equals, and you would want to either write or at least mentally view this as being the same thing as sine of x to the 1/2 power. So you'd bring down the 1/2, the power would reduce by 1 and become a 1/2 power. And then the chain rule says you'd come inside and say derivative of sine is cosine. And then technically speaking, and we're going to see why today, you won't have to write it down, but at least in my head, I would come inside and say, well, the derivative of x is 1. And you could clean it up. You could rewrite this with the cosine of x on top, the 2 on the bottom, that's from the 1/2, and the square root of sine of x on the bottom. And you may be thinking, why'd you say times 1? Well, whenever I am taking a derivative, I'm moving from the outermost function and moving inwards. In other words, I would look at this and see my outermost function is the square root function, or the 1/2 power. So that's why that's the derivative that you see first. Next, inside of that is the sine function. That's why you see its derivative next. And inside of that is an x, and its derivative is 1. So you may be thinking, again, why write the 1? When you move from outside to inside, isn't the very last thing always going to be a 1? And since multiplying by 1 changes nothing, why would we do it? Well, it's because of implicit differentiation. Let's say we were looking at a circle. For the sake of simplicity, let's say we have a circle centered at the origin with a radius of 5. Well, the equation of that circle would be x squared plus y squared equals 25. If you wanted to know what's the equation of the tangent line right here at the point at which we have, say, maybe a 45-degree angle or something like that. And of course, since this is calculus, shouldn't be saying 45 degrees. No, that's a sin. We should be calling that a pi/4 angle. So what do we need to be able to find that tangent line? We need to be able to find this slope. Find this slope, we need a derivative. But the problem is, when I try to solve for y here, it's not super difficult, but it has one problem associated with it. When I solve for y, what ends up happening, because of the way roots extract, you get a plus or minus on there. So what this means is that there are two different versions, two different parts to this solution. There's the positive part, which if you were to put this in your graphics calculator, you would see it plots out the top half of the circle. Then there's the negative part. Put that into your calculator and you'll see that it plots out the bottom half of the circle. So could I, theoretically, just take the derivative of this one and use it to answer this question? Well, I could. But this time it was not extremely difficult to solve for y. There will be times when you just don't want to, or you just can't solve for y. So instead of solving for y and taking the derivative of the correct version of the equation, I need to just step down here and learn how to take the derivative of it without ever having to solve for y in the first place. And we do that with implicit differentiation. And to be able to perform this implicit derivative, again, something I've mentioned before, something you have to remember. You have to always be aware and keep focused on what's a variable, what's a constant, and what's a function. All right, so let's take this derivative. After much preparation, let's go ahead and do it. Here I'm going to use the power rule. Derivative of the second power is to bring a 2 out front, take the x, drop it to the first power, and then take the derivative of the x itself, which is a times 1. And again, you're saying, why was that necessary? Why do we even do that? Well, about to show you. Now, derivative of y squared. Again, power rule. 2 comes down, power drops to 1, times derivative of the y. All along we've been saying derivative of x is just a 1, but when we take our derivatives implicitly and it's time to take the derivative of y, it's not a 1. Derivative of y is not a 1 because y is not a variable, y is a function. Derivative of the x variable, yes, it's a 1. Derivative of the y function is dy dx. And the derivative of 25, since it's a constant, is just a 0. So there's the difference. There's why I'm always trying to teach people to take the derivative using the chain rule all the way down to the last step. Because again, the derivative of an x is a 1 because x is a variable. Derivative of y is y prime, or dy dx. So what we will do, clean this up a little bit. And if you want to practice using other notations and simplify this, we'll take that dy dx and it's called a y prime. And now I need to solve for y prime. So I'll move the 2x to the other side. Divide by 2y. The 2's cancel. And there you have your derivative. And this is different, this is new, but your derivative is defined in terms of not just x, but x and y. All right, so what I will need to do, if I want to find the slope at some point, I need the x and the y coordinate of that point. All right, so how could I find an x and a y coordinate? Let's just, instead of using this point, let's just come down here. We know that this thing has a radius of 5, so it goes out as far as 5 here, up as far as 5 there, over to -5 here, down to -5 there. And so let's just grab a point. All right. As a matter of fact, let's grab one first where we know what should be happening. What we know is that down here, gun instinct tells us that should be a horizontal line. That slope should be 0. What I know about this point is it is the point 0, that's your x value because you're on the y-axis, -5. All right, so plugging that in, y prime at 0, -5 would be y prime equaling opposite of x over y, which turns out to be 0. So that slope turned out exactly as we suspected. Okay, that is exactly what we should have expected to see happen. All right, so at this point, at least, it's doing what we thought it ought to do. All right. Okay, so let's try a point here. This is somewhere else it ought to be doing exactly what we think it should, what's obvious. So putting a tangent line there, we would say that y prime at the point 5, 0 is y prime equaling, again, it's an x, which was a 5, over, that's the opposite of x, over y, which at this point is 0, which is undefined, which again is exactly what we thought it ought to do. So since this slope was 0, and the equation of a horizontal line is in the form y equal to, we conclude that this is a y equal -5 on this one. This is undefined, and an undefined slope has an x equal to format for its equation, so this is an x equal 5. All right, now, we've got those done. Those are pretty clear. They did exactly what we would have suspected. Let's look at this point right here. Okay, what would that point be? Well, it's on the triangle at a 45-degree angle, or a pi over 4 angle, with a radius of 5. So that would be 5 square roots of 2 over 2, comma, 5 square roots of 2 over 2. Okay, so y prime at 5 square roots of 2 over 2, comma, 5 square root of 2 over 2 would be y prime equaling the opposite of x over y, which would be a -1. Again, is that a surprise? It really shouldn't be. I mean, we hit it right out here where it has a 45-degree angle. Shouldn't be a surprise that that's what it turned out to be. So the equation of that tangent line would be y minus 5 square root of 2 over 2 equaling -1 times x minus 5 square root of 2 over 2. All right. I'm writing the equation in that form. It's a little bit different. We don't do it like that every time. But an advantage to this form, instead of like a slope-intercept form, for example, is I can clearly see the slope. It's right here. And I can see the ordered pair that was used to create the equation. All right, so if you need to represent it in such a way as to be able to visually inspect the ordered pair that was used, this is a good technique. All right, this is a good style for that. All right, so let's do some more implicit differentiation. The thing to remember when you're doing implicit differentiation is that the derivative of x is 1 and the derivative of y is not 1. The derivative of y is y prime. So if I had an x squared plus an xy minus a y squared equals 4. And you are asked to find, and the instructions will say something to the sort of find dy dx, what you'll be told to do. All right, we'll do it. Derivative of x squared is a 2x. That's the power coming down, reducing to 1, times a 1. Plus, this xy will require a product rule. Okay, first, derivative of second plus second derivative of first. There's your product rule. Minus derivative of y squared is a 2y times a y prime, and that's equal to a 0. Because 4 is a constant, and derivative of a constant is 0. So here's what I'm going to want. I'm going to want everything that's got a y prime in it to stay on the left. That's here and here. Anything that doesn't have a y prime needs to go to the right. So x, y prime stays on the left. Minus 2y, y prime stays on the left. Equaling a -2x because it moved from left to right. And a minus y because it moved from left to right. Factoring out the y prime. And finally dividing to finish the solving. There is your dy dx. Written in another symbolism, but there it is. All right. Now, let's look at this and do the same thing, but mix in perhaps a slightly different type of function. Look at something a little bit different. Let's say I had sine of x plus cosine of y equaling sine of x times cosine of y. Another good example of why implicit differentiation is needed. Good luck solving for that y right there. It would not be impossible, but why would you if you don't have to? All right, we're going to differentiate it just the way it sits. Derivative of sine is cosine. Derivative of x is 1. Derivative of cosine is negative sine. Derivative of y is not 1. It's y prime. Over here on this side, a product rule. First, and then derivative of the second. Plus the second times derivative of the first. Okay? Once again, everything that's got a y prime in it needs to be on one side. Anything that doesn't have a y prime needs to go to the other side. So negative sine of y, y prime stays on the left. Now I'm going to have a plus sine of x, sine of y, y prime that comes to the left, equaling a negative cosine of x plus a cosine of y, cosine of x. Again, factoring out a y prime, and perhaps writing this in a slightly better arrangement. And finally, solving for y prime. And there's your y prime. All right. Again, would it have been possible to solve for this y and done this in a more direct fashion? Actually, it would have been possible, but that's not the point. That is not the point. The implicit differentiation, again, can be used in lots of situations to simplify a lot of different kinds of derivatives. As a matter of fact, one derivative, one group of derivatives in particular, that this is very useful and it really finds a lot of good use, is your inverse trigonometric functions. For example, if I had y equal arc sine of x, and I needed to take the derivative of arc sine of x, how would I do it? The absolute best way, by far, is implicit differentiation. I would take the sine of both sides of this equation, and I would get sine of y equals x, and it is from there that I would take the derivative. Derivative of sine would be cosine of y times a y prime equals a 1. Derivative of x is 1. And y prime would be equal to 1 over cosine of y. Now, we have been in the habit of basically just leaving it at that. But in the case of the inverse trig functions, we want to be able to take the derivative and give an answer in terms of just x instead of an answer in terms of y. It's just advantageous. All right? So, what's the cosine of y? Okay, what would the cosine of y be? Well, let's draw a picture, and we can see if we can figure that out. If we draw an angle, all right? If we draw a triangle, a right triangle, the thing we have to remember in this original equation is what does x represent and what does y represent? Well, in a normal trig function, if you were to take the sine of something, what are you taking the sine of? You're taking the sine of an angle, right? Normally, you take the sine of an angle, and out comes a ratio, okay? Therefore, when you take the arc sine of something, what you're taking the arc sine of is a ratio, and what's coming out is the angle. This is something to bear in mind. So therefore, in this case, right here, that's the angle y. right there. That's what this is telling us, is that this is an angle. And this x is a ratio. We're going to write it as a ratio. We're going to want to stick a 1 underneath it. What ratio is it? It's the sine ratio. All right. And with the sine ratio, that means that the x is playing the role of the opposite side, and the 1 is playing the role of the hypotenuse. Therefore, I need this missing side. All right. So Pythagorean theorem says that 1 squared is equal to x squared plus, we'll just give it a question mark for a second, plus the question mark squared, that missing side. And therefore, question mark squared equals a 1 minus x squared. Therefore, question mark is the square root of 1 minus x squared. That's a really horrible, amateurish way to write that, but what the heck, we're just having some fun. So that side by the Pythagorean is the square root of 1 minus x squared. All right? And again, remembering, y is the angle. This is side x. This side is a 1, and here's this side. We're being told that y prime is 1 over the cosine of this angle. Okay, 1 over the cosine of this angle. Well, the cosine of angle y, if you remember, is adjacent over hypotenuse. Therefore, the reciprocal of that would be 1 over square root of 1 minus x squared. And so there we have, with the help of the drawing of that right triangle, we have discovered a way to express y prime, which is the derivative of the arc sine function, in terms of x and only x, which again is very advantageous. We could do this 5 more times, and what we would find using the same procedure is the derivative of all of your inverse trig functions. I don't recommend you do this 5 more times. You can if you really, really, really want to. But the best thing to do is simply memorize them. And if you're wondering, am I going to have to memorize a whole lot of derivatives? Yes, yes you are. And so here's the next 6. Derivative with respect to x of the arc sine function is 1 over the square root of y minus x squared. The derivative with respect to x of the arc cosine is 1 over the square root of 1 minus x squared with a negative sign out front. And you're going to see this pattern a lot. Derivative of a trig function, inverse trig function versus its inverse co-function. One will have the negative where the other one does not. That's very typical. So for derivative with respect to x of the arctan is 1 over 1 plus x squared. The derivative with respect to x of the inverse cotan is still the 1 over 1 plus the x squared, but as I sort of hinted, it's got the negative out front. Derivative with respect to x of the arcsecant is going to be a 1 over x, the square root of x squared minus 1. And finally, with respect to x, the inverse cosecant, it's got the 1, it's got the x, it's got the square root of the x squared minus 1, but what do you think it's going to have? A negative out front. Okay, it's going to have the negative out front. These need to be memorized. You need to be able to recite them instantaneously, and I will mention that for whatever reason, that one gets a lot of mileage. You'll see that used a lot, not just in this class, but the one after and the one after that. The derivative of the inverse, the arc tangent, gets a lot of mileage. So make sure you have them all memorized and be prepared to use that one extensively. It's a lot of use, so have them all memorized.